Denormalization can give us significantly better performance. So let's take a look at some of the characteristics of denormalized tables. Well, data is often redundant. So for example, here in this example, looking at a books table, we have author information that's duplicated as well as publisher information. We may have non-atomic values. So for example, some analytical databases allow and actually encourage the use of structs or structures to have more complex values within a column than simple atomic values. And then we also tolerate transitive dependencies. So if we have, say, a value that's dependent solely on a non-key attribute in the table, and that non-key attribute is itself dependent on the primary key, that's totally fine. Again, it violates the third normal form, but we're willing to tolerate that because in exchange for not being normalized, we're going to get significantly better performance. And really the critical thing is, in analytical databases and analytical applications, we are typically at a reduced risk level with regards to anomalies. And that's because of how we work with the data. We have relatively few updates. So while customers might, constantly be updating their orders and their baskets and things like that, in an analytical database like a data warehouse or a data mart or say just a data science database, we typically load the table once and then maybe update it or add data, but rarely do we go back and correct data that, say, for example, we loaded a week ago. Now, if there are mistakes in the data, we may correct a batch or delete a batch and reload with corrected versions. But outside of errors in data loading like that, we typically do few updates. Really, we're more likely to be writing new data and reading data. Now, oftentimes we do batch inserts, and those batch inserts go through an extraction load transform or extraction transform load process. So the data transformation is already kind of cleaning up the data, massaging it, and getting it into, sort of our preferred form. So in that case, again, there's less risk of, say, an update anomaly. Again, unless, say, our transformation process broke, but that would be a significant event, and we would hopefully catch that with our monitoring system. Now, sometimes we also have streaming inserts, and those are relatively simple data structures. So you might think of like an IoT sensor that's measuring temperature and humidity and maybe some other environmental measures, and then transmitting those, say, every minute. And so it might be a relatively simple structure that has a sensor ID, a timestamp, and then whatever the measures are. So again, it's fairly simple. With IoT data and streaming data, again, you typically don't update it. And another thing about like IoT data, which is typically used in the aggregate, even if you did have a mistake, even if there was an error in one of the readings in one of the minutes, if you're getting 60 readings per hour and you're aggregating those, it almost doesn't matter in terms of the aggregate values. So if you're looking at statistical measures across these data structures, very small errors just kind of get washed out, and it actually doesn't make a material difference the way we report on it. So again, a data error may occur, but it doesn't have as much of an impact as it would in an OLTP system. And another thing that happens, we eliminate the need for really complex joins. So that's particularly useful with regards to simplifying and speeding up performance. Now, there's a couple of different ways that a denormalized database may look. A common way of building denormalized databases that's been popular for over a couple of decades is the star schema. And here the idea is we have this fact table with a bunch of measures. For example, they might be all the measures that an IoT sensor is taking. And then we have different dimension tables. And the dimension tables may be things like, the sensor information and geography information and a time information, so we can keep track of like hours within days, within weeks, within years, and be able to easily roll up data. So that's one way of denormalizing. And this is commonly done in databases where you have a row level orientation. And row level orientation means when you go to read a data block, you read an entire row at a time. And that makes perfect sense when you're dealing with OLTP systems, because if you're going to update something in a customer record, you're likely to maybe want to update multiple things. So it's helpful to have the entire customer data block available to you. Now, in analytic systems, when we're reading, we're typically reading a few columns across many rows. So a more performant way to work with it is using columnar orientation or using a columnar format. And in that way, when we go and we read data blocks, we're actually reading many different attribute values from different rows, but all from the same column. So if you want to do an average, say, of the temperature measure of a particular sensor over a 24-hour period, it makes a lot of sense just to grab the temperature data, grab the temperature column, and not bring in the other data that you're not interested in. And that's what columnar data stores do for us. Now, another common denormalization technique is to have what's called a wide column table. And here you can imagine what some data modelers in the relational as their worst nightmare, which is that we denormalize, we put everything into a single table and we make it very wide. Now, this would be incredibly problematic for an OLTP system. It's actually quite advantageous for many analytical systems. And the really high volume, large scale data warehouse systems, the kinds that scale to petabyte scale, like Google BigQuery or Google Bigtable, will use a wide column model. Now, Bigtable is a NoSQL database, but BigQuery is an analytical database, and it uses SQL for querying, and it uses this kind of wide column model as well. Now, the advantages of denormalizing are that it can be easier to query. Again, we're getting rid of complex joins, so we don't have to join table A to B to C to D to E and introduce the risk of making mistakes in our complex queries. Queries can also be more efficient. Again, there are a lot of reasons for that. We discussed columnar versus row. That's just one example. And it also simplifies load procedures. Oftentimes with ETL processes, we can do joins sort of in stream and then write to a single table. It also makes it easier if you're dealing with something called slowly changing dimensions and you want to keep track of history. Well, by actually tracking the data in a row by denormalizing, you don't have to worry about tracking multiple records in, say, a dimension table and then pointing to the correct version of the data. So again, denormalizing can somewhat simplify load procedures. One of the most effective ways